Ever just wonder about stuff like how did everything come together?
Yeah.
Like how did atoms even start forming bonds to make, well, everything?
Yeah, it's pretty wild when you think about it.
Well, we're going to try and unpack some of that today.
Yeah.
Um, all because one curious user out there had honestly, this kind of crazy idea about light and atomic bonds.
Yeah, and it's a pretty intriguing idea, to be honest, especially when you consider the sources we're looking at today.
Right.
So we've got some excerpts from a ChatGPT conversation where this idea popped up. And then we've also got this Wikipedia article on something called diffraction spikes.
Diffraction spikes.
Yeah.
Okay, so I'll be honest. When I first heard about this whole thing, like I was picturing, atoms like clinging together to form molecules and all that. And then suddenly I'm seeing these like dazzling starbursts, these diffraction spikes. And I'm thinking, how are these two things even remotely connected?
Right. Well, that's what's so fascinating here. You see, this user, they noticed the same kind of similarity between the spikes and these bond diagrams.
Yeah.
And they started wondering, could light, which we know existed even before atoms, could it have somehow played a role in how those bonds formed?
Whoa, okay, so light before atoms. That's a big concept.
It is. And the really interesting thing is, ChatGPT, when asked about this, it actually confirmed that, yep, light did predate atoms. And it even cited the cosmic microwave background radiation as evidence.
Okay, now hold on. Cosmic background radiation, it's like the echo of the Big Bang, right? The leftover energy from that whole event.
Exactly, yeah. It's this incredibly faint light that just kind of fills the entire universe.
Mhm.
And it basically tells us that light was already there, like way before atoms even started forming.
So are we talking like Big Bang happens,
Yeah.
then there's this primordial light, and then much later, atoms start to form and bond together?
That's the general timeline, yeah. So it's really kind of mind-blowing to think that light, this fundamental force of the universe, might have been around to sort of set the stage for everything that followed.
That's a wild thought. Like light was, I don't know, like the first actor on the cosmic stage or something.
Yeah. And if you really go with that idea, then it's not that far-fetched to imagine that, this early light might have somehow influenced the very rules of how atoms interact and form those bonds.
Okay. So I'm starting to see where this user was coming from, but let's go back to those diffraction spikes for a sec. Can you like paint a clearer picture for our listeners of what they are and how they form? Because I'm still a little fuzzy on that.
Sure. So imagine you're looking at a bright star through a telescope, or maybe even just in a photograph. Now, instead of seeing a clean, crisp point of light, you actually see these streaks of light that radiate outwards, kind of creating a starburst pattern. Those are the diffraction spikes.
Oh, okay. I think I've seen those before. But how do they form?
Well, basically what happens is light bends or diffracts as it passes around obstacles. So in telescopes, it's often the support structures for the secondary mirror that cause this diffraction. Or in cameras, it can be the shape of the aperture, especially when it's narrowed down.
It's like a side effect of how the instrument is built, basically.
In a way, yeah. But the interesting thing is, even though it's a side effect, it still creates these really beautiful and symmetrical patterns. And that's where we get that connection back to the atomic bonds.
Ah, okay, yeah, I remember the user noticed that symmetry, right? That the spikes spread out from a central point, just like how atoms arrange themselves in a molecule.
Right. It's like you're looking at this visual echo of the fundamental building blocks of matter.
But hold on, light creating those spikes, that's one thing. But how could it possibly influence something as tiny as an atom?
Well, that's where things get really mind-bending. To understand that, we need to dive into the world of quantum mechanics.
Oh, quantum mechanics. Sounds complicated.
It can be, yeah, but it's also incredibly fascinating. One of the key concepts here is what's called wave-particle duality. And that's basically the idea that light can act as both a wave and a particle.
So light is kind of like two-phased. It changes depending on what it's doing.
Yeah, it's kind of like a chameleon. And
Yeah.
this duality has these really profound implications for how light interacts with matter at the atomic level. It means that light has this extra layer of complexity that that we're only beginning to understand.
Okay, so we've got light acting as both a wave and a particle. How does that tie back to atomic bonds?
Well, it's still a largely unexplored area, but some scientists believe that light's wave-like properties could influence how quantum states form within atoms. And
Hmm.
those quantum states, they basically determine the allowed energy levels and configurations of electrons within an atom.
So are we saying that like the wave-like nature of light is actually influencing the the blueprint for how atoms are structured, like how they're put together?
Imagine it like this. Think of a wave, like a wave passing through a pool of water.
Yeah.
It creates these peaks and troughs, right? And
Mhm.
imagine those peaks and troughs influencing where electrons are more or less likely to be found within an atom.
Oh, I see. So the wave-like properties of light are kind of shaping those probability zones for the electrons, and those zones then in turn influence how the atom bonds with other atoms.
Exactly. It's a great way to visualize it, and it really suggests that light could be more than just a passive observer in the formation of atomic bonds. It could be an active participant, Like it's actually shaping the very fabric of matter as we know it.
Okay, so we've been talking about this wild idea of light influencing how atoms bond, but there's got to be more to the story than just atoms linking up, right? I mean, I vaguely remember from like high school chemistry that there are different types of bonds, like covalent bonds and ionic bonds.
Yeah, you're absolutely right. There are different types of bonds, and that's where things get even more interesting when we start thinking about light's potential role in all of this. So in covalent bonds, what happens is atoms share electrons to become more stable. It's kind of like they're pooling their resources, to create this stronger connection.
And then ionic bonds, that's where one atom basically donates an electron to another,
Hmm.
and then that creates this sort of like electrical attraction between them.
Exactly. One becomes positively charged, the other negatively charged, and then they attract each other like tiny little magnets.
Right, right. Okay, so we've got these different types of bonds, but how does light fit into all of this?
Well, remember how we were talking about light affecting the energy levels of electrons and even the shapes of those electron orbitals?
Yeah.
Well, those factors, they're actually crucial in determining what type of bond forms.
So are you saying that depending on how light interacts with those electrons,
Mm.
it could actually be like nudging them towards forming one type of bond over another?
Mm.
Like it's influencing the chemistry between atoms?
Yeah, that's exactly the idea. So, for example, with covalent bonds, for those to form the electrons from each atom, they need to be able to share the same space, right? Their orbitals have to overlap.
Right.
But the shapes and the orientations of those orbitals are influenced by the energy levels of the electrons. And we know that those energy levels can be affected by light.
Oh, I see. So light could be like helping to create those perfect conditions where the orbitals can overlap and a covalent bond can form,
Hmm.
like it's, I don't know, like a cosmic matchmaker or something.
That's a great analogy. And the same principle applies to ionic bonds. The energy that's needed for an atom to lose or gain an electron and become an ion, that can also be influenced by light.
So light might even be determining which atom becomes the giver and which one becomes the taker in that whole ionic bond exchange.
Exactly. Yeah. And that brings us back to this idea of light acting as a template for atomic structures. It's not just the overall symmetry of the molecule, but the types of bonds that form, the specific arrangement of the atoms within that molecule. All of that could potentially be influenced by light.
Wow, it's like light is shaping the language of chemistry, like dictating how atoms how they communicate and connect with each other.
That's a great way to put it. And it leads us to another really fascinating concept, and that is resonance.
Resonance. Okay, now that sounds familiar, but I can't quite place it. Is it like a vibrating tuning fork or something?
Not quite, although the idea of vibration is definitely relevant here. So in chemistry, resonance describes a molecule that can't be represented by just one single structure. It's like the molecule has these multiple possible arrangements of electrons and bonds, and each one kind of contributes to its overall stability and behavior.
So it's like the molecule has a split personality, and each personality has a slightly different take on how the electron should be arranged.
I like that analogy. That's a good one. So now light comes into play here because those wave-like properties we've been talking about, they can interact with these different resonance structures, and they can actually stabilize some more than others.
Oh, so light could be influencing which of those molecular personalities is the most dominant, like it's conducting the orchestra, choosing which instruments play the loudest.
Yeah, that's a really valid analogy. And if we take a step back, it really makes you wonder, what are the implications of all this? If light is influencing the very structure of molecules at this fundamental level, does that mean it's also shaping the properties of materials and maybe even life itself?
Okay, now that is a huge thought. Are there any like clues out there that this is actually happening?
Well, there are some really tantalizing hints that are emerging from various fields of research. One example is photochemistry. That's basically the study of chemical reactions that are triggered or influenced by light.
Oh, okay. So like photosynthesis,
Yeah.
where plants use sunlight to make energy.
Yeah.
That's a type of photochemistry,
That's
right?
that's a classic example, yeah.
Yeah.
But photochemistry goes way beyond that. It's
Mhm.
it's involved in everything from the formation of smog in the atmosphere to the development of new materials that respond to light in very specific ways.
So light isn't just like illuminating our world. It's actively shaping it, changing it at the molecular level.
Precisely, yeah. And the more we learn about photochemistry, the more we realize just how pervasive and powerful light's influence really is. It affects everything from the colors that we see to the functioning of our own bodies.
It's incredible to think about. Like we're living in this world that's constantly being salted by light, and we're only just starting to appreciate its artistic touch, I guess you could say.
Yeah, and it all goes back to that initial observation that sparked this whole deep dive. Those diffraction spikes that resemble those atomic bond structures. What might have just seemed like a curious coincidence could actually be a hint of a much deeper connection.
It's mind-blowing to think that those starburst patterns in photos could
Mhm.
be a glimpse into the very forces that shaped the universe as we know it.
Yeah, it really speaks to the power of observation and the interconnectedness of everything in the cosmos, and it makes you wonder what other hidden connections are out there just waiting to be discovered.
Speaking of discoveries, I'm really eager to hear what other insights you have in store for us as we continue this deep dive. What's next on our agenda?
Well, so far we've been focusing on how light might influence atomic bonds, but there's another really fascinating side to this story. And that is how atomic bonds in turn can influence light. It turns out that the way atoms are bonded together, it can actually dramatically affect how they interact with light, and that leads to some truly remarkable phenomena.
It's amazing to think about everything we've talked about so far. Like how light could actually be shaping the bonds that literally hold our universe together.
It is pretty mind-blowing.
But now we're kind of flipping the script, where we're going to look at how those bonds can actually influence light. It's like this cosmic dance, this back and forth between light and matter.
Yeah, exactly. We've seen how light can shape the way that atoms connect, but those connections they also dictate how a molecule interacts with light.
Okay, that makes sense. But why should we? I don't know. Like, why should we care how atomic bonds affect light? Does it have any real world implications?
Well, think about it this way. Our entire world, it's built on how light interacts with matter. I mean, we see because light reflects off of objects. We use fiber optic cables that transmit, light signals. Even lasers for surgery or entertainment, they all rely on this interplay between light and matter.
Right, right. And all those things depend on how light interacts with the matter it encounters.
Exactly. And that interaction, it's determined in large part by how the atoms are arranged within a material. The types of bonds they form, the whole molecular structure. It's like each molecule has its own unique way of interacting with light based on how its atoms are connected.
So the way that atoms are bonded together,
Yeah.
it can actually dictate how a material absorbs light, reflects light, maybe even emits light.
Precisely, yeah. Each molecule, it has a unique fingerprint, you could say, when it comes to light. And understanding that fingerprint is key to so many scientific and technological advancements.
Okay, I'm starting to see the bigger picture here. Can you give me a specific example of how this works in the real world?
Sure. Let's start with something that we all experience every day, and that's color.
Color. Okay.
So the reason that we see different colors is because different molecules, they absorb and they reflect different wavelengths of light. And what determines which wavelengths are absorbed or reflected?
It's got to be the atomic bonds, right?
You got it. The arrangement of atoms and their bonds.
So if a molecule absorbs certain wavelengths of light, then the remaining reflected light is what creates the color that we see.
That's a great way to put it. Yeah. And even tiny changes in molecular structure, they can cause these really dramatic shifts in color. I mean, think about a red rose compared to a blue violet. Those differences in color, they arise from these very subtle variations in how the atoms are arranged within their pigment molecules.
Wow. So that the very language of color is written in the bonds between atoms.
Exactly. And this principle, it goes way beyond color. It affects everything from the transparency of materials to the efficiency of solar cells. The structure of a molecule, it dictates how it interacts with light.
It's incredible how profound this connection is. Do you have another example, maybe something a little more, I don't know, high tech, to kind of really bring this home?
Sure, let's talk about lasers.
Lasers. Okay.
So lasers, they work by exciting atoms to a higher energy level, and then when those atoms drop back down to their grain state, they release these photons of light that are all in sync with each other, and that creates that really focused, intense beam of light.
Right, right. And those laser beams, they're used in so many applications now, from scanning groceries at the checkout to like incredibly precise eye surgery.
Exactly. But the key to creating a laser is finding a material that has the right atomic structure
Yeah.
to support that whole process. And this is where understanding atomic bonds becomes absolutely crucial.
So scientists are essentially designing materials with specific atomic arrangements to create lasers with the properties that they need for specific tasks.
Precisely. It's like molecular architecture, where we use our knowledge of atomic bonds to build materials that interact with light in very, very specific ways.
It's amazing that we're actually harnessing these fundamental forces to create technologies that improve our lives.
Yeah, and it all circles back to that interplay between light and atomic bonds. The more we understand about this relationship, the more potential we unlock for new discoveries and innovations that we haven't even dreamt of yet.
This whole deep dive, it's really given me a whole new appreciation for light, for atomic bonds, and for that intricate dance between the two. It's amazing what a simple question can lead to.
I agree. It's been a fascinating journey.
And to our listeners, we hope this deep dive has sparked your curiosity and inspired you to see the world in a new light. Literally, remember the universe is full of wonders just waiting to be discovered if we just take the time to look closely and ask the right questions.
Yeah, keep exploring, keep questioning, and never stop being amazed by the intricate and interconnected nature of our universe. Until next time.